All right, well, discrete math, what is up? Um, so here's the deal, guys, just so that you know where we're at. Um, you know it's an elective class. You know it's an elective math class. None of you need it to graduate. Grade from third quarter is not going to change, other than to go up if you want to work on some of the older stuff. So really, everything from here on out, it's just kind of up to you. But hey, that's how it's always been. So just kind of keep that in mind as we're going through this stuff. You wouldn't be taking this class if you didn't think that it was at least somewhat interesting. So I'm going to continue to present stuff to you. I'm going to continue to give you opportunities to do homework, to take quizzes, to check your understanding. There is going to be a midterm that will cover all of this stuff, midterm number 2. That is a chance for you to get a better grade to replace your first midterm. And then don't forget too, I'm also going to offer you a final exam that can also take the place of that first midterm. So don't think that all this stuff is just going to go to waste. And just besides it being interesting, it might end up actually helping out your grade a little bit. So that being said, we're going to kind of jump into chapter 13 today. We're going to talk about what are called Fibonacci numbers. You will at some point need a graphing calculator, so if you want to get that ready to go, feel free to do that. I'm just going to kind of talk you through these slides, and then you'll have a chance to maybe even start some of the homework. So Fibonacci sequence, here that is for you. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 33, and it continues to go on forever. You might just take a moment, if you've never seen this before, look at those numbers, see if you can figure out what the pattern is. It's a little bit different than maybe something you've seen in some other sequences. So take a little bit of time, maybe pause the video to think about it. And if you haven't found it out yet, don't worry, we're going to talk about it. So the sequence of numbers above called the Fibonacci sequence, and the individual numbers in the sequence are called Fibonacci numbers. Fibonacci sequence is infinite, and except for the very first two ones, every single number in the sequence is the sum of the two numbers before it. So if you didn't figure out the rule, there it is for you. So to kind of illustrate that for you a little bit here, first thing is the first two numbers are 1, 1 plus 1 is 2. So then the next two numbers are 1 and 2. 1 plus 2 is 3. So your next two numbers are 2 and 3. 2 plus 3 is 5. Next two numbers then would be 3 and 5. 3 plus 5 is 8. And you just keep doing that forever and ever and ever. Okay, so there's the idea, there's the pattern behind it. So in order to talk about Fibonacci numbers, we're going to kind of lay out some ground rules. We're going to denote every Fibonacci number by using the letter F for Fibonacci and a subscript that indicates the position that it falls in the sequence. For example, F sub 1 is 1, F sub 2 is also 1 because the first two numbers are 1. F sub 3 is 2, the 10th number, F sub 10, would be 55, and we don't know what it is yet. We're actually going to find it in a little bit. The 100th Fibonacci number, at the very least we can call it F sub 100. A generic Fibonacci number is usually written as F sub n, where it represents the position. There's going to be two other ones that we'll talk about. F sub n minus 1, which is the number 2 places, or 1 place before n, and then F sub n minus 2, which is 2 places before F sub n. That's really what we're going to use to kind of clear up the formula for the Fibonacci sequence. So the rule that generates your Fibonacci numbers is the recursive rule, because it defines the sequence based on the earlier numbers in the sequence. Using that subscript notation that we just had talked about, the formula for that is that F sub n is equal to F sub n minus 1 plus F sub n minus 2. Still one thing that's missing though. It requires that you have two consecutive numbers, Fibonacci numbers, before it can be used. So it can't be used on the first two numbers. We just have to define those. So F sub 1 is 1, F sub 2 is 1. Those are going to be our anchors, or kind of our key, or our seed, if you remember the idea of a seed, for our Fibonacci sequence. So here's kind of that summarized for you, the recursive definition. The two seeds, F sub 1 is 1 and F sub 2 is also 1, and then you use those to start the recursive rule. Okay, so cranking out some big numbers. How are we going to find that value of F of sub 100? If you wanted to, if you had the time, and I guess some of you maybe do, in a calculator, you could just use that recursive definition to crank it out. So just to kind of skip through some of those, I'll get us started with f sub 97, which is that number beginning with 83 and a lot of other numbers there. As you can tell, not even to 100 yet, and it's a very large number. Okay, then you get to f sub 98, which is an even bigger number. And then f sub 99, which is an even bigger number. And then by the time you finally get to f sub 100, you get to this ginormous number. If you convert that into dollars, so consider that to be kind of cents, divide by 100, it's a lot of money. To give you an idea of how big it is, if you were to take 100 billion for yourself and then divide everything else that's left between every single man, woman, child on Earth, about 6.7 billion people, every single person would get a little more than $500 million each. That's a big number. But you can probably tell that using that kind of recursive formula, not necessarily a fun way to do it. It turns out in 1736, our good old friend Leonard Euler, who you probably remember from Unit 5 when we were talking about Eulerizing graphs, actually discovered a formula for Fibonacci numbers that didn't rely on previous Fibonacci numbers. Unfortunately, that formula was lost. But the good news, it was rediscovered 100 years later by a French mathematician and astronomer, Jacques Binet, who somehow ended up getting all the credit, as the formula is now known as Binet's formula. Here is that formula, and in fact, I'm going to show you how to use it here in just a moment. But if you wanted to write that down, that is the formula that you could use to figure out what those terms in the sequence are. We're going to actually use a graphing calculator to kind of work through this. So here are the steps. So write these down, pause the video, and then I'm going to be switching to my calculator on screen to kind of show you how to work through this. So if you wanted to find the nth Fibonacci number, especially for large values, the first thing is you're going to type in 1 plus square root of 5 divided by 2 and store that as a variable a. You're then going to compute a to the power of whatever number you want to find. So if you wanted to find the third Fibonacci number, which is 2, then you would put in n is 3. If you wanted to find the fifth Fibonacci number, which is n is 5, then you would type in n is 5. We're then going to divide that result by the square root of 5, and then when it becomes necessary, we'll round to the nearest whole number. That'll actually give us f sub n. Okay, so let's do it to, instead of doing f sub 100, let's do a smaller one. Let's just do f sub 5 for right now. So we're going to look for the fifth number, which the fifth number you could probably just find as easily by hand. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. So the fifth number, f sub 5, should equal 5. But this would be a good way to check to make sure that this formula works before we try to do it for something much larger. All right, so grab a graphing calculator. Let's go through it. So with graphing calculator, here's what you're going to do. You're going to type in parentheses 1 plus the square root of 5 divided by 2. It's going to give you a decimal. It's about 1.62. You're then going to store that as a variable. So to store it as a variable, you're going to hit the store button right here, and then just pick any letter you want. The PowerPoint uses A, so I'm going to store that as A. So hit alpha and then math to get that letter A. Press enter, and it'll just give you that same number. But now it's been stored as A. We were looking for the fifth Fibonacci number, so we're going to take that variable A to the power of 5. It's going to give you 11.09. And then to get our Fibonacci number, only thing we're left to do, divide by the square root of 5, and it tells us that our answer is 4.9596. All you have to do, round to the nearest whole number, which is 5. There is your number. Now, if you remember that Fibonacci sequence, 1, 1, 2, 3, 5, the next number is 8. So if we do this for 8, let's see if it works. That would be the sixth number in the Fibonacci sequence. So we're going to take now a to the 6th power, so alpha a power of 6, which is 17.94. Divide that by the square root of 5, round to the nearest whole number, which is, hey, look at that, 8.02 to the nearest whole number is 8. it's kind of cool, this formula that we've got to be able to figure out those numbers, especially for very, very large numbers. So continuing on, this is going to kind of take us through, if you want to do it for f of 100, or f sub 100, so same idea. Calculator again gives you that 1.62. You then would raise it to the power of 100, and your calculator wouldn't give you all these decimals. It would give you about the first 9, and then it would cut it off. And then you divide by the square root of 5, and you should get this number. Again, you wouldn't even have to round because your calculator wouldn't be able to give you all of that, but that would be how you could get some very large Fibonacci numbers. So why would we even talk about it? Who cares, other than it's just kind of a cool sequence? It actually turns up they show up in nature quite a bit. One example is with certain varieties of flowers. For example, lilies and irises have 3, which is the fourth number in the Fibonacci. Buttercups, columbines have 5. Cosmos, anemones have 8. Yellow daisies, marigolds 13. English daisies, asters 21. And you can see how there are many more that continue with that pattern. So kind of interesting. Some other places where they get used, the spiral around a pine cone, actually kind of interesting there. The center of a sunflower is kind of cool. Some other places, obviously we talked about those. I don't know if we talked about an artichoke, but it turns out that around an artichoke, the Fibonacci number is in the rows. Here's a picture showing a pineapple and how it works to be the scales that spiral around the pineapple. And then the sunflower, how they kind of spiral out from there, actually turns out to be the Fibonacci sequence. So just a few more pictures, kind of some cool stuff for you guys to check out on your own. I think that's all I've got for you on this first day back. So thank you if you were able to watch that whole video. I appreciate it. We've got a few more sections in this chapter to kind of talk about. We'll continue with those. I'll get some more videos uploaded. By now, all the notes in terms of PDFs should be posted for you. Homework's been posted, and we've got our quiz scheduled for Friday. That'll be a multiple choice quiz just to check your understanding and see how well you are at making sense of kind of what we're talking about this week. So have a good one, guys, and I will talk to you soon.